The universe is expanding, but it's expanding even faster now than it was doing before. Dark energy is the name given to that unknown mechanism causing the accelerated expansion. However, recent observations suggest that we might have been all wrong about dark energy and it might be something completely different. Now, what is dark energy? Well, we don't know, hence the dark. However, what it does, pushing the expansion of the universe, is something that we can model by adding a constant in Einstein's equations of general relativity. And it's really a funny story because Einstein's theory predicted the universe to be dynamic, so either expanding or contracting. But the leading view back then was that the universe is static. So Einstein added this ad hoc constant to make the universe static. Later, the observations by Hubble suggested that the universe was indeed expanding. So Einstein took that constant out of his equation, regretting the decision of adding it by calling it his biggest blunder. Because he could have predicted an evolving universe, a missed opportunity. However, it didn't stop there. Decades went by, but in the 1990s, we found that the expansion rate of the universe is not slowing down. On the contrary, it is speeding up. And we don't know why. Think of it this way. If you throw a ball up, you would expect it to eventually slow down, stop, and come back. But what we were seeing in the universe was that essentially the universe is just expanding faster and faster. Like gravity, the everlasting effect of gravity should be pulling all these things together. But there was something more. Dark energy. We don't know what dark energy truly is, but what it does, well, pushing the expansion of the universe, is something that we can model via adding that constant, cosmological constant, back into the equations of general relativity. And what does this cosmological constant mean physically? Well, it's really a constant energy density. And the most famous interpretation now is vacuum energy, so energy of empty space. As the universe expands, you get more of this energy, hence the accelerated expansion. So this was mostly what we thought about dark energy. And as you might have noticed, it doesn't really have to be the cosmological constant. Like all we know is that the expansion rate of the universe is accelerating and something's there. Is it truly cosmological constant? We don't know. Cosmological constant can explain it, but well, there can be other things as well. And that takes us to now. Recent observations, particularly from the Dark Energy Survey and Dark Energy Spectroscopic Instrument, have hinted that maybe dark energy is not really a constant. When combined with the data from the cosmic microwave background, these surveys show mild preference for an evolving dark energy, weakening slightly as the universe ages. Though more data is needed to really call it a discovery. So that would mean that the constant cosmological constant might not be as much of a constant. And that's potentially a big deal because so much of what we can say about the universe comes from what we believe and assume, decide to focus on, and what we neglect to be insignificant. Now, the most popular and successful, if you can say that, model for how the universe evolves is the Lambda CDM model. And I know the terminology can be quite out of the blue, but it will make sense. Here, lambda stands for the cosmological constant. Here, constant is the important part. So, a constant energy density, a constant dark energy. CDM stands for the cold dark matter, so a particular kind of dark matter. And it assumes some other things that are acceptable to some extent, like homogeneity and isotropy. Assuming all that and more, we can make certain predictions as well as predictions about the universe. And Lambda CDM model had been pretty good in matching reality. Not all the way, but very close. So it predicts a flat universe, cosmic microwave background, Big Bang nucleosynthesis, the large-scale structure of the universe, and more. Obviously, we wouldn't make something of a default model if it wouldn't lead to, our universe to some extent. But what if dark energy isn't a constant, as a recent study points out? What if it's dynamic? Well, in that case, the assumptions of this model wouldn't be correct. And so we have to start anew. For instance, there was this idea of quintessence, which essentially explained dark energy as another quantum field, giving us a variable dark energy. Also, last year, there was this idea of timescapes that completely got rid of dark energy. And no, I'm not saying Lambda CDM has to be correct. On the contrary, it most probably isn't the right model, and there were hints even before. The most famous one is the infamous Hubble tension. And it's really a related idea. Like, how we are saying the expansion of the universe is accelerating? But if you were to ask exactly how fast is the universe accelerating, we don't have a consensus. Broadly speaking, there are two ways of figuring that out. One is the standard candles method, in which we use recent data observations of the recent universe and we get a number for how fast the universe is expanding. And the other method is by using the theory, the model that we have, so Lambda CDM. And these two methods simply don't agree. This famously has been dubbed the crisis in cosmology. So maybe there's something wrong with the data or with the model or both, we don't really know. But what I'm trying to say is that there were doubts on Lambda CDM even before. And it's not like, okay, so dark energy is dynamic, so this updated model would fix everything. Well, it can, but it hasn't yet. Still, the idea of a dynamic dark energy would give a lot more flexibility for fitting the observations, as dark energy would have different strengths at different times. Almost everything that you believe about the universe comes from the model that you choose. If you believe that dark energy is the cosmological constant, you get entirely different predictions compared to if it is dynamic. The most important, probably, is the eventual fate of the universe. In a universe with constant dark energy, so a cosmological constant, the leading view is that the universe would continue to expand more and more, but then the everlasting increase in entropy would render everything to decay. So stars, black holes, everything would simply decay in the slow heat death of the universe. But if dark energy is dynamic, well, it then gets a bit more interesting, and we can't really say much because, well, it could be that it weakens further, even flipping its direction, in which case we may see the universe expanding to a maximum size and then contracting. So a fan favorite big crunch may be possible, and even the big bounce. But if it later decides to strengthen up, well, in that case, we may get what's called a big rip, in which the everlasting accelerating expansion may rip everything apart. So what's happening with dark energy? Well, we don't know. It is showing signs of being dynamic, but it's one of the deepest questions in all of physics. And the progress in the last couple of years, and maybe in the next few years, would be revolutionary in our understanding of the true nature of dark energy. Now, just to be clear, the data yet hasn't made it conclusive that dark energy is dynamic. Further data is required to cross that threshold or vanish the claim entirely. And with new telescopes like the Euclid, the Rubin Observatory, and the Roman Space Telescope coming online soon, we may not be in the dark for long. Thanks for watching.